My name is Keith. This is a water quality irrigation suitability data set predicting whether water is suitable for irrigation to help support small-scale farmers that are irrigating their crops for using lakes and rivers by taking readings of physical chemical properties such as salinity, turbidity, pH, dissolved oxygen, electrical conductivity, among others, whose concentrations determine a lot the quality of the water they are using to irrigate their crops. So I'll take you through. So this was basically a South African water data set we are working with, collected from 3 biosphere reserves, and it's a time series data set, meaning that for every meaningful reading we take will be determined at different sets of actions we perform at different points in time. So the temporal trends, trend plots will confirm the seasonal variation in water chemistry per biosphere. And as such, some of the key decisions we took during cleaning was that we realized we were working with a 48 sample data set that had 119 non-suitable samples and then 361 suitable samples that gave us an imbalance ratio of 3:1. We also had some sense anomalies detected, and then we dropped the nitrate, phosphates, and salinity. And we also, our domain check where the pH was greater than 14, temperature greater than 50%, dissolved oxygen, we dropped all these and set them to null before applying any median imputation.
By the name is of Chigoz Alan. We'll be talking about the models we used. So our goal was to classify each water sample as either suitable or non-suitable for irrigation. To do this comprehensively, we trained and evaluated 13 different models covering every major family of the machine learning algorithms. On the linear side, we used the logistic regression as our baseline. Then for the distance-based learning, we used the k-nearest neighbor. We included the Gaussian naive Bayes for probabilistic classifications. Then for the tree-based methods, we trained decision trees, both pre-pruned and post-pruned, using cost complexity pruning. For the assembled methods, we used random forests and extra trees. The bagging side, an XG boost, gradient boost, and other boost on the boosting side. We also used the support vector machine with an RBF kernel. And finally, we trained 2 neural networks, a shallow single layer network and a deeper theory layer network with batch normalization. Every model was trained using the grid search cross-validation with 5-fold cross-validation. So we're always selecting the best hyperparameters without touching the test state. Because our data was imbalanced, about 75 suitable and only 25 not suitable, we applied SMART to the training data. SMART created synthetic minority class samples, increasing the not suitable class from 96 to 288 training samples. We evaluated every model on a held-out test set using the 12 metrics. Our top performer was the XG Boost, achieving an F1 of 0.993 and an area under curve of 0.9994. The highest growth, all of the 13 models. As you can see in this next slide, that XG Boost was the highest across all of the models that we had used.
My name is Murijo. Today I want to take a closer look on the critical element in our project. How geographical location directly impacted our model's prediction performance. So, starting with this regional overview on my screen, we analyze data across 3 different biosphere reserves. And to see how exactly location influences our prediction. The differences we found were quite amusing. As you can see from my graph, Hembe shows the highest suitability rate of 94%. In contrast, Kruger and Mariko came in with 69 and 64 respectively. So, what this variance tells us that water quality and environmental factors differ significantly across these regions. And it proves that we cannot just rely on one assumption for the entire region. So moving to next slide, at our geographical area patterns, it helps us explain the why behind the other numbers, the 94, 69, and the 64. So we mapped our where model was missing the mark, and we discovered that the majority of the misclassification were heavily clustered right in the Kruger area. Specifically, these errors occurred at the riverside due to the fluctuating error sensor readings. On the other hand, Heyman predictions were mostly good and correct because the chemistry there was constantly stable and good. Unfortunately, the geographical insight revealed from this lesson, or from what we observed, it tells us to explain that location alone wasn't enough for our model to be accurate. It relies on a deeper water chemistry, and this exactly explained and helps us to come to the realization that we need to analyze data by geographical bias testing.
My name is Nalvega Shadia, and my presentation will focus on whether the model can generalize to new regions, whether it is biased by the location, and which water quality factors drive its predictions. So first of all, our first objective was to determine whether the model could perform well on the biosphere reserves it had never seen before. And to test this, we use the Leave One Biosphere Out validation, or the LOBO. And in this approach, the model is trained on 2 biospheres and tested on the third unseen biosphere. The results remained consistent across all regions with the mean F-score around 0.94, which indicates that the performance did not collapse when an entire biosphere was removed from the training. So this means that the model learned meaningful water chemistry relationships rather than simply memorizing the location. And on the other part, we looked at whether the model relied on geographic information as the shortcut. The first thing we did was to remove the GPS-related features, which was the mitigation A. We removed the GPS-related features such as the latitude, longitude, and then the altitude. This forced our models to rely on the water quality measurements only. Even after removing these features, we see that the mean F1 score remained at 0.9405. And the second mitigation, which was mitigation B, was balancing the training data. Since Kruger contributed most of the samples from the we unsampled the smaller biospheres to reduce the imbalance, and the mean F1 score remained high at 0.9378. We also performed the chronological split, where we trained on the oldest 80% of the records and then tested on the newest 20% of the records. The F1 score dropped by only 0.012, demonstrating strong temporal stability. And then after that, we see that the model maintained performance across all the tests, showing that it learned the real water chemistry patterns rather than the location shortcuts. So on the next slide, we are going to look at on the next slide, we are looking at the SHAP analysis, how it helped to explain the model's decisions. So across all the 3 biospheres, the most influential factor were the pH and the dissolved oxygen. In Kruger, we had high pH and low dissolved oxygen. This can be solved by adding fertilizers and reduce upstream organic pollution. And then in Mariko, we see particularly severe dissolved oxygen issues, making it the most critical region. And then in the third region, which was the Vimbe, we also exhibited consistently low dissolved oxygen levels, indicating a need for aeration treatment before irrigation use. So these findings do not only explain the model's predictions, but also provide practical recommendations for improving the water quality. And in summary, I would like to say that the model generalizes well to the unseen regions. It's not biased by the geography, and it remains stable over time. It provides explainable insights that can support water management decisions.
I'm Elizabeth again, and I'm going to present findings and recommendations. So for explainability, we use SHAP and LIME. When you look at the global feature importance, this I extracted out for XGBoost and for decision tree. So the pH in range and the pH heavily outperformed the other matrices across all the tested algorithms. So meaning the models perfectly recovered the standard FAO water safety threshold of 6.5 to 8.5, and our secondary predictive drivers were log conductivity for salinity risk and then biosphere encoding for regional baseline water chemistry. Then when we look at a line, we realize that when pH is actually moving towards the positive, low conductivity is pulling towards the negative. This is crucial because it tells how uncertain the model is. So it's important for the farmers before they begin irrigation. Then we also looked at how can we improve the water. When there's low pH, we recommend that we apply agricultural lime, and then when the pH is high, we can apply elemental sulfur. For high salinity risk, we recommend that probably we can add more water or use crops that are tolerant to salt. So, and then for low oxygen, we can reduce upstream organic pollution. Then for deployment, XG boost was our best, so we recommend that we deploy XG boost for its productive accuracy. So we can actually pair it along with the cost complexity prone decision tree as a transparent rule-based fallback that extension officers can easily interpret and trust in the field. Thank you for listening to us.